Good afternoon, and welcome to the 2008 Alice Louise Reynolds Lecture, Women in Scholarship Lecture. I am Randy Olson, Universal Librarian of the Harold B. Lee Library. It is our distinct pleasure to have with us today Professor Jani Radebaugh from the Department of Geological Sciences, who will deliver an address entitled Encounters at the Edge of the Solar System, Exploring Jupiter, Saturn, and Beyond. We'll hear more about Professor Radebaugh in a moment. The Alice Louise Reynolds Women in Scholarship Lecture is a memorial to one of BYU's most outstanding female scholars. Professor Alice Louise Reynolds was the first woman to teach college-level literature classes at Brigham Young Academy. When it became BYU at the dawn of the 20th century, she was the first woman to become a full professor. The current Harold B. Lee Library can trace its beginnings to a committee on library development and cultivation on which Professor Reynolds served, first as a member and then for 19 years as its chair. As a devoted teacher of comparative literature, she dedicated her efforts over many years to fulfill the dream of having a large and comprehensive university library at BYU. For example, she was instrumental in raising funds to purchase all 1,200 volumes of Provost Judge J.W.N. Whitcotton's large and diverse personal library, which was the nucleus around which the Harold B. Lee Library has grown. At her death in 1938, the library had expanded to 100,000 volumes, a noble beginning to our present-day collection of 4.3 million books. Today's library stands as a perpetual memorial to her vision and dedication. The Alice Louise Reynolds Women in Scholarship Lecture was established to honor this remarkable scholar, teacher, and friend of the library, and to recognize the continued contributions of outstanding female scholars at BYU. These outstanding scholars are memorialized in a room in the library that has been named after Alice Louise Reynolds. It is through the generosity of the now-defunct Alice Louise Reynolds clubs and the current Friends of the Library that an endowment for this lectureship has been made possible. Following Professor Radebaugh's address today, we will be pleased to have a brief question and answer session. Now to today's featured speaker, Professor Jani Radebaugh. She is a true scholar. She received her Bachelor of Science degree in physics from BYU in 1993, and then completed a Master of Science degree in geology at BYU in 1999 before heading to the University of Arizona, where she received a PhD in planetary science in 2005. Her research focuses, among other things, on the moons of Earth, Saturn, and Jupiter. Using data from the interplanetary Cassini and Galileo survey missions, she has examined mountains and volcanoes in Io and Titan. In 2005, she was among a small number of scientists who traveled to Antarctica to search for meteorites whose fragments hold clues to the structure and composition of the solar system. Her terrestrial work has taken her to such disparate locales as Death Valley and Kilauea in Pincantes, Mexico, where she studied earthbound volcanism to better understand the processes on Saturn and Jupiter's moons. She is a member of the American Geophysical Union Division of Planetary Sciences and the American Astronomical Society. She is the author of several refereed articles on the surface features of planetary moons and has made several conference presentations around the world. Professor Radebaugh is also a caring teacher and a mentor to her students. She truly represents the best in the legacy of Alice Louise Reynolds. It is with great pleasure we welcome today's Alice Louise Reynolds Women in Scholarship Lecturer, Professor Jani Radebaugh.
Thank you very much. It is a great pleasure and honor to be here. I was so interested to read about Alice Louise Reynolds and about her history and legacy. She did a lot of work in addition to all the things that were mentioned about her scholarship. She also did some political work. And you can imagine as a woman doing political work in the early 1900s, what do you think she worked on? Well, women's suffrage, of course. So she had great influence all around the country in addition to all the wonderful things that she did here at BYU. The title slide for my talk today is lifted almost directly from a movie poster. It's a documentary by Werner Herzog, who has accomplished many other wonderful documentaries. And what I want to emphasize in this title are a couple of things. One is the word encounters. I want to try to keep things personal and help you understand my own experiences in explorations of the solar system. And also we use the word encounters when we describe what a spacecraft does when it interacts with another solar system body. It encounters it. as it flies past it. So I thought it was apt. The original title is actually Encounters at the End of the World, and it is a documentary about Antarctica. And that's also fitting because I went there a few years ago, and I'm actually leaving again in a week to go back to Antarctica. I didn't learn the lesson the first time, I don't think. So anyway, but I won't talk about Antarctica today. I'd like you to keep in mind the subtitle down here too, Off the Map, Things Get Strange. So remember that once we leave Earth, things become very otherworldly. I also will not talk about this image here. This is an image taken by the Mars Reconnaissance Orbiter HiRISE camera. And this is a camera that was designed and built by my graduate advisor at the University of Arizona. And this image was obtained last spring as the Phoenix spacecraft was descending onto the surface of Mars. And some of you might remember that Phoenix spent the summer on Mars, and it did many wonderful, successful experiments looking for water and water ice. And this image was obtained, and this is a zoom in of a much larger image. Someone had to very carefully look through this image and find the tiny little white dot that you see in the box there. And as we expand from that dot, we notice that it's actually the whole Phoenix spacecraft, complete with parachute and even parachute threads that we can see from this other orbiter orbiting Mars. I think it is one of the most spectacular images that we've obtained in solar system imaging. I also won't talk about this picture. This is an image taken by Messenger in a flyby of the planet Mercury, and this was also obtained earlier this year. And this spacecraft is working on getting to a point where it can orbit Mercury. It will take it a couple more years to be able to do that. But as it flies past Mercury, it tries to take new images as it goes by, and this was a brand new image taken. And this crater that you're looking at here up in the corner is about 100 kilometers across, about 60 miles, and you can see the bright ejecta coming from this crater, and the crater is not named. It's such a large crater, and you can tell by looking at the limb of Mercury here, you can see the curvature, and Mercury's bigger than our own moon, and yet this crater is not named, and that's because we've never seen it before. So we're still obtaining images of solar system objects that we've not yet seen before. It's a wonderful time to be doing solar system research. I'll also only spend just a couple of slides on Pluto. Poor Pluto. It's just received so much bad press, so much good press. I guess any press is good press, and Pluto has received its share over the last couple of years. But this is a recent image of Pluto. I'd like to help you understand why it is that we don't call Pluto a planet anymore. This is Pluto next to its moon Charon, and it's also next to a couple of other little moons, Nix and Hydra, that were only discovered a few years ago. This is a Hubble Space Telescope image. And one thing to remember is that when we first saw Pluto in the sky, we saw it together with its moon Charon. And so we thought it was a much bigger object than it actually is. And not only that, we have discovered many other objects far out at the distance that Pluto is from the sun, which is about 60 times the distance that the Earth is from the sun. And many of these objects are very big. You can see this one in the upper left. This one is actually now called Eris. And we have this other one, Sedna, and a couple of other objects too that all kind of fit into the same category that Pluto does. So we wondered what to do with them. Do you call them all planets, or do you create a separate category for them because they have very different characteristics from the other 8 planets that we normally talk about? And in fact, that was the decision. But to kind of ease the blow, we've decided to call them Plutoids. So Pluto still has a strong presence. And while we've been making these decisions, the New Horizons spacecraft has been busily heading toward Pluto, regardless of the decision we made, or not. So New Horizons will arrive at Pluto in 2015. Keep in mind that its launch was 2006. So the solar system is a very big place, and it takes us a long time to get to some of these locations. I also won't spend any time at all on Uranus, our 7th planet from the sun and its entourage of icy moons, or on Neptune with its beautiful methane-rich atmosphere and very interesting moon Triton. But I hope that you'll hear more about those 2 objects in the coming decade or so at least. We're thinking seriously about trying to go back to these 2 places and to study them more carefully. What I will spend most of the time on my presentation today will be on a couple of moons in the solar system, or satellites of other planets. These 4 up at the top are satellites of Jupiter, And they're the four largest satellites. They're called Galilean satellites because Galileo discovered these with his telescope. And this is Io, Europa, Ganymede, and Callisto in order outward from Jupiter. I'll talk mostly about Io, but also just a little bit about Enceladus, Europa, just in from Io. And I will also talk about Titan, which is a moon of Saturn. And all of these objects are shown here to scale with the moon, our own moon here, to help you understand just how big they are. Notice that Io is about the same size as the moon, and Titan is much bigger. It's the size of Ganymede, this object up here. Both of these are about the same size as Mercury, just to help you understand. The Galileo spacecraft orbited Jupiter and all of its moons from about 1995 until 2003. And fortunately for me, this was right during my graduate studies, both at Brigham Young University and also at the University of Arizona. When I arrived at the University of Arizona, I was arriving at kind of the tail end of the Galileo mission. It had accomplished all of its main mission goals and was still working, so we kept it orbiting and decided to fly closer to Jupiter, which means that we could actually fly past Io, which is very close to Jupiter. And so I got to study brand new data from Io as a graduate student, and I had a great fortune to be able to do that. Io is the most volcanically active body in the solar system. This is a picture of a volcanic eruption occurring right here in the center of this caldera on Io's surface, and is shooting up a plume of gas that you can see rises up above the surface of Io up to about 300 or 400 kilometers. So these plumes come out with a tremendous amount of velocity and distribute materials to a great distance. The deposit that you see right here from the plume eruption is about 1,200 kilometers in diameter, about 800 miles across. These are very large eruptions, and they're occurring all over Io's surface. This is an almost true color picture of Io. This is something you would see if you were to fly past it in your own spacecraft. And you can see lots of black pockmarks all over the surface, and these are the results of active eruptions of lava, a little bit like the same kind of lava you would see on Hawaii if you were to go to those volcanoes. And you can also see a lot of kind of roundish circular features. These are more plume deposits from eruptions that are ongoing. So Io's got a lot of active volcanism occurring this very minute, and it's because of its interactions with Jupiter that it's very close to, and also the other satellites that are out from Io, from Jupiter. And these play a game of tug-of-war with Io, and they heat up its interior, allowing for it to have active volcanism. My student Brandon Barth is working on looking at all of these calderas on the surface and trying to categorize them according to their level of activity. This helps us understand the interior of Io. And it's similar to a project that I did for my own dissertation, trying to understand the distribution of volcanoes on Io. Here's a close-up of one of the volcanoes we see. This caldera right here, which is green in color, we call them golf courses sometimes, it's just what they look like. And this is about 30 kilometers across, and you can see a whole bunch of different colored lavas coming out, and this is due to the fact that there's a lot of sulfur on Io, and so when sulfur and sulfur dioxide gases come out of these volcanoes, they colorize the surface. So we try to understand the interaction between gases and lavas, and so it's a little bit like volatiles of any kind. A volatile on Earth that's common is water and lava. So this past summer I got to go to Iceland for a meeting, and was very blessed to be able to go on a field trip up to the top of a glacier and to look at this volcano called Grimsvatn. And this is erupting through the glacier, and because it erupts through the glacier, it's very explosive when it erupts, and it deposits these big layers of ash. And then we can see that later when there's been a collapse in the center, so you can see layers of ice that have been deposited from snowfall during that year, separated by a layer of ash because of a volcanic eruption that occurred. So this is a nice analog for Io, and this is something we try to do in solar system studies. We go to places on the Earth that we can actually walk up to and study what those analogs to these solar system bodies are like, so that we can better understand those locations. This is one of my favorite volcanoes on Io. It's a caldera. It's about 80 kilometers across, about 60 miles across. And you can actually see that there is lava pooling up in the bottom of this caldera. It's acting a little bit like a lava lake, only it's very big. So this is another thing we try to go and visit on the Earth. This is one I'd love to go to. It's in Ethiopia, called Erta Ale. You can imagine it's a little bit difficult to get to these days. So we keep waiting to see if we can actually get there. But this is a good analog for this feature that I just showed you previously on Io. We can, however, go to the Big Island of Hawaii fairly easily. This is a group of NASA scientists that I went to Hawaii with in 2003, I believe. And we actually walked out on the lava flows and carried some instruments with us. And this was my function here. I was pack mule. I think that's a telescope I'm carrying in the back there. And we bring those instruments that are fairly similar to the ones that we have orbiting Jupiter, or we did at the time, and try to do analog studies from up close. And so we'd go out at night and take images of the lava flows at night. And then we'd also do a few kind of fun studies during the day. This is me scooping out some lava. And you can actually walk right up to the lava flows on Hawaii and pull the lava out. So it's a really wonderful experience if you ever get a chance to do that. We try to go there often with BYU geology groups when we can. It's a very good experience for students. So why do I show this picture of Hawaii? Well, this is actually a view I had once after receiving some news. The Galileo spacecraft was working so much past its own, deadline, its own mission, prescribed mission. And as I said before, we were able to orbit closer to Jupiter and be able to fly past Io. But as a result, we were bathed in the really harsh radiation belts of Jupiter because we were so close to Jupiter. And it really did a lot of damage to the electronics of the spacecraft. So one instrument in particular, the camera that I was concerned with, kind of had a lot of difficult phases. It would blip in and out because of all the charged particles bombarding the instrument. And so we never quite knew if it was going to work just right during each flyby. And we would very painstakingly plan for what regions of Io to look at with the spacecraft as it flew past. And we would get very excited about these new regions that we'd be able to see with the spacecraft. And then the instrument would go into safe mode and it would turn to Earth and say, what do I do? You know, something bad happened. And then it wouldn't take any pictures of Io. So I was flying to Hawaii during one of these observations for some field work. And I called my friend just as I arrived in Hilo on the Big Island. I said, how did we do? And he said, oh, it went into safe mode and we lost all the observations. So I just laid on a bench and underneath the palm tree and cried. It was just so sad. And I wonder if, I may have been the only person to fast for a spacecraft. Probably that's not true, but at least I know I did, so. Galileo was also able to take some pictures of Io's sister moon, Europa, and we have great interest in Europa because it's got an icy crust. It's made of water ice. And then we also think, based on some images and also some other data, don't these look just like icebergs that have rafted apart from each other? And we think that's exactly what has happened. It's almost like sea ice. So we have a rigid outer layer of water ice, and then we have a liquid ocean underneath. And if we have a liquid ocean underneath, then there must be an ocean floor. It's probably in contact with rocks. And so it might behave a little bit like black smokers on an ocean floor. So our long distance plans are to eventually send a lander to be able to find its way through the ice and then swim down through this liquid water ocean and maybe go find some black smokers on the seafloor. And there is perhaps a good place to go and look for life, for evidence of life. And this is a big goal of NASA, that NASA has, is to be able to go and find life or evidence of prebiotic molecular activity in the solar system. And in fact, this is one of two missions that are being discussed currently at NASA for where to go in the outer solar system. And the decision on these two missions will be made probably in January or February of this year. And this is one of the leading contenders, and this is a Jupiter Europa orbiter. Plan to actually launch a spacecraft to orbit Europa and study it very carefully and plan for going there to land on the surface. This will cost about $2.5 billion. It's a lot of money, a lot of taxpayer money, and I would say it's well worth it to be able to go and learn these things about the solar system to help us better understand our own Earth. I also want to talk to you today about Amazing Saturn. This is a nice kind of old-fashioned movie poster style advertisement for the Cassini-Huygens mission. You can see that written up at the top right. Cassini, which is about the size of a bus, you see all these people down here for scale. This was launched in 1997. Took about 7 years to arrive at Saturn. Was launched at night, and a friend of mine watched this launch and said that the clouds, as the spacecraft went up into the clouds, just lit up just like a Japanese lantern. And on its way to Saturn, it flew past Jupiter and obtained tremendous amount of data at Jupiter and also at Io. And there's a graduate student working with me here in physics who's studying a whole bunch of these images that you can see on the right. This is a picture taken of Io at night. So all of the light that you see coming from Io is from its volcanoes. So we can actually use the light from the volcanoes to be able to tell just how hot the volcanoes are, and that helps us understand what the volcanoes are made of, how they erupt, and we can do this over timescales of just a few minutes, and that was impossible with Galileo because we'd only do a quick flyby, take a few images, and then wait for several months before the next one again. So Cassini really revolutionized our understanding of Io and the Jupiter system. So Cassini went into orbit around Saturn in 2004, and as it did, it began to obtain beautiful images of the Saturn system that far surpassed anything that we'd seen with Voyager. Voyager was wonderful in its own way, but we had newer, better, faster instruments, and so we've just had reams of wonderful, amazing data, especially pictures and images of Saturn and its satellites. I'll show you a lot of those images here. This is one of my favorite pictures from the Cassini mission. This is actually only possible from a spacecraft. And if you think about where the sun is in this image, it's directly behind Saturn, then you'll understand why we had to have a spacecraft to be able to take this picture. And we can see the atmosphere and the rings all illuminated. This is a little bit enhanced so that you can see these details better. If you zoom way into one of these rings, right up here, you see this tiny little dot. Any guesses as to what this is right here? This is actually the Earth and the Moon. And we can see that from Saturn's orbit. So it's a really wonderful connection between Saturn and the Earth that we can obtain with this spacecraft. This is an image of one of its little icy moons in front of Saturn. It's a little bit hard to puzzle through this image until you understand what's going on, but this line right here is the ring plane of Saturn, and so that means all of these up here are shadows from the rings projected onto Saturn, onto Saturn itself. So this helps you understand just how thin the ring plane is. It's only about 1 kilometer thick, but it's many thousands, tens to I think maybe even 100,000 kilometers wide. So the rings are just extremely blade thin. And they contain mostly water ice particles, ranging up to blocks the size of houses, down to just very small particles. They're organized into a neat set of coherent rings that all seem to have different brightnesses and different densities. And these are all controlled by tiny little planets called shepherd moons that come in and help keep the particles in each of their respective rings. This is another image of a moon or a shadow cast by Saturn onto its rings and a bunch of its tiny little satellites right here. We were able to obtain a few sets of images so that you can see little movies. Here's one of the larger icy satellites of Saturn, and a couple of other little small ones racing past it. And this is just due to differences in perspective of the spacecraft for each of the satellites. So this may not want to try to digest this whole thing, but just so that you understand how these things are ordered, there are a bunch of tiny little moons close to Saturn, and then a couple that we'll talk in a little more detail about, Mimas, Enceladus, Tethys and Dione, just a little bit bigger. These two are about 500 kilometers across, about 1,000 kilometers across for Tethys and Dione. Rhea and Iapetus, 1,500 kilometers across. And then this giant Titan, and remember this was about the size of Ganymede, so a bit bigger than our own moon. And then we've got Iapetus and Phoebe. Enceladus is a very interesting moon. It's very close to Saturn, about three Saturn radii away. So just imagine how big the radius of Saturn is and then put 3 of those next to each other, and that's where Enceladus is. And then here's a picture of Enceladus with Great Britain for scale. So it's very small. And in fact, it's so small that we would expect that it would have been long dead or long cooled off, because very small objects radiate away all of their heat and then they cool off very quickly. But in fact, we are surprised to find that the surface of Enceladus is active. In fact, at the South Pole right here, we can see jets of water coming out of Enceladus. So that means that its interior must be hot. And in fact, when we look at some regions that we call tiger stripes, big cracks in the ice, we can tell from other instruments that they're fairly warm, and that when we say fairly warm, we mean not 100 Kelvin, which is a couple hundred degrees below freezing. This is how cold things are in the outer solar system, but just above 100 Kelvin, so it's a little bit warm compared with the actual surface of the object. And so we hypothesized that the interior of Enceladus is being massaged, again, perhaps because of Saturn being so big, and there's a little bit of tidal massaging going on, and that keeps the interior warm. But people are still working through models for how this happens and how you can maintain it over the lifetime of the 4.5 billion-year-old solar system. But we noticed that what this does to the surface, and this again is a water ice surface, it expands it and cracks it, so we have these nice big beautiful giant cracks. This image was only taken in October of this past year. There's another big giant crack. And there are still a few craters on the surface, impact craters, that litter the surface as a result of other bodies whizzing through the solar system and then smashing into the surface. This is an extreme close-up, also taken in this past October. And what we can see here is the very active tectonism that goes on the surface of Enceladus. So here are a bunch of faults. There are some oriented in this direction, some are oriented in this direction, yet others are oriented this way, and all of them manifest a different episode of stretching or contracting, mostly pulling apart the surface of Enceladus itself. And this is pretty close to the source of one of those giant geysers of water that comes out of the bottom. I think that it might be just off of this image here, but related to this really big crack. And actually, just a little bit of a side note, when I worked here as an undergraduate student, I worked with Doug Jones, and we worked a bit on Saturn's magnetic field. And there were some puzzles about Saturn's magnetic field that I think still exist, that Cassini hasn't completely answered. But we were looking for some kind of a plasma, some kind of a bunch of particles that could be somewhere in the vicinity of about 3 times away from Saturn, 3 Saturn radii, that would be able to do some things to the magnetic field, mask the real signature of the magnetic field. And then it turns out with Cassini, 10 years later, that we find that Enceladus is very active and is spewing lots of particles out into this giant ring around it that we call the E ring for Enceladus. And so here's our plasma, finally surfaced about 10 years later. This happens quite a bit in all of science, but especially in planetary science. We have just a few select data sets to work with. We can only make a few hypotheses at the first, and then we go back and make new observations that help us understand what we were seeing before. I also want to mention a researcher. His name is Steve Ostrow. He's very intelligent, and he's working right now with Cassini radar observations, and has just submitted a paper yesterday. And he talks about how there are deposits on the backside of Enceladus that are very fresh and bright from new radar observations. And so very interesting new observations that he's made there. Okay, so there are a couple of other satellites. I'll just show you a few images of these as we go. This one almost looks like a sponge. We think maybe what has happened is there are some dark particles that have collected on the surface of this object, and then they've melted their way through the ice, made kind of like little ice cups. And you might see those as you're out hiking up on Mount Timpanogos or somewhere else, where you see where a little dark pebble has melted its way through the ice. There's some giant cliffs on some other bodies, again due to expanding and contracting of the body as it cools. This object, Iapetus, is very interesting because this is about how it would look to your eyes. It's very dark in most places, but then it's also got some bright material as well. And the dark and the bright are very different from each other and very dramatic. In fact, we got some close-up images with Cassini, and we asked ourselves a couple of times, is it dark over light, or is it light over dark? Which one is covering, the other? It's a little bit hard to tell which is covering the other. And as I was in Iceland at Grimsvatn, I noticed this in a couple of different locations. Again, I was thinking to myself, Iapetus, because of these images I'd seen before. And what would you say for the upper left image? Probably dark over light in that case. And for the lower right image, probably light over dark. And yet the two are related to each other in many ways in terms of their formation. And it turns out that for Iapetus, we probably also have a little bit of both going on. So sometimes you need to keep your mind open to a lot of different options. We think there's a complex example of sublimation of ice and then redeposition of it on a different hemisphere, perhaps also related to some deposition of dark material from the orbit of Iapetus, but that's related in many ways to these terrestrial analogs that we see. This little moon, Phoebe, actually orbits Saturn at a very great distance, 200 times Saturn's radius. And we think, based on its orbit and also the composition of its surface, which sometimes we can get from spectral analyses, that it might actually be a captured Kuiper Belt object. And a Kuiper Belt object is just what Pluto is. And so Pluto and those other family of objects that I showed you before are all part of this region beyond Neptune in the solar system that's made up of mostly icy objects, but with also a decent amount of rock to their composition as well. And Phoebe matches these very well. So this attests to the kind of dramatic and interesting place that the very early solar system was, because we think a lot of these objects whizzed around, interacted with each other, got sent out of orbit in one location and maybe captured in another. And this seemed to happen quite a lot in the outer solar system. This is a close-up of Phoebe. It's got a whole lot of impact craters on it, so it's a very old object, a very old surface. In fact, this is another example of how impact cratering is very important in the solar system. You almost can't pick out a spot on this moon Tethys that doesn't have an impact crater on it. And it's a little bit like Mimas down here in the lower right. You just can't help but think of it as the Death Star. It just looks like the Death Star moon. So, and these are both impact craters, the result of one object hitting another. What I'll spend the rest of my time today on is Titan. And this was the best view that we had of Titan with Voyager, which was there in the mid-1980s. All we knew about Titan is that it was covered in a haze-enshrouded atmosphere. And we could also tell this from the ground. We had telescopes that could actually see all the way to Titan and tell us that the atmosphere was made mostly of nitrogen. Sound familiar? That's a lot like the Earth's. And also that there was a whole lot of haze in the atmosphere. This is organic, rich haze. So it's almost like a smoggy day in Los Angeles, both in terms of composition and color and everything else. So, but that's about all we knew about Titan up until we had new observations from Cassini. So before, we knew that there was methane in the atmosphere as well. And methane is something that should actually dissociate quickly. The sunlight comes in and breaks up that molecule, and so it should go away very quickly. Maybe one way to replenish it is through volcanism. And so we thought about that for what happens on Titan. We also know that the atmosphere has complex organics, and then we also know that there's perhaps an energy source. Because of its orbit around Saturn, we think that it is acted upon by Saturn in the same way that Io is and Enceladus, so that maybe there's a little bit of internal heating. And then also if we have this volcanism that replenishes the methane, then that's also related to internal heating. So then also we think that there's good evidence that there's a liquid water sublayer that's likely. Therefore, Titan is a good place to go and look for what we call prebiotic chemistry. We don't want to say go there and look for life, because we'll likely be disappointed if we do that, right? But if we go and look for precursors to life, we don't really understand how life arose on the Earth. So if we go to these places and study this in action, or study the system as something that's failed or that is only now starting, then we can better understand what has happened on the Earth. We assumed because of the methane in the atmosphere that Titan would be a little bit like Earth. Because we have water in Earth's atmosphere, occasionally it rains out on the surface and it fills up lakes and oceans. So we thought that might happen on Titan, and that we'd have lakes and seas of methane. So the Huygens probe, which was attached to the Cassini spacecraft, is built by Europeans, detached from Cassini and went down through the atmosphere of Titan to land on its surface. And it was given the capability of being able to splash down into some lakes, because we kind of expected that would happen. But in fact, as it came down, it did see large river channels. This was maybe unexpected. River channels carved into bedrock of water ice. So the rivers are made of methane, and the rock is made of water, but it's ice. So it's a very different and unique location, although this looks a whole lot like Earth, doesn't it? And as it landed on the surface, it landed in something that was probably a dry riverbed, and with rounded cobbles and pebbles that look like they've been rolled around in a stream bed, just like you might see in the desert Southwest. Other instruments took a careful look at Titan and have been doing so since 2004. Cassini just barely finished its prime mission this past summer, and it is in its extended mission, which should go for another 2 years. And we're even planning the extended mission, which would go for 7 more years after that, and may even place Cassini into an orbit where it could sit right inside the ring plane, the inner ring plane in Saturn, before it is sent into Saturn to be destroyed. So keep watching to find out what happens with Cassini. It will be an interesting story, I think. So this is Titan seen by other instruments. We're able to design instruments to peer down through the haze and through the atmosphere. And we notice that it's a land of light and dark. There are dark terrains, there are light terrains, but we didn't really understand what they were. Another instrument on Cassini, the radar instrument, has been very valuable in helping us to see more clearly what the geology is like on the surface of Titan. And this is an example of a radar image. They come in these long, thin noodles because they're obtained as Cassini flies past Titan, and it adds up this whole image as it flies past. And we have, I think, close to 20 of these now for all of Titan's surface. And we see things like impact craters and river channels. Radar images are a little bit like a negative real image. The bright here means that it's really rough, and so it's often the more mountainous features. And then dark usually means smooth, and those happen to be kind of the lower areas on Titan. We've been studying dunes on Titan. We actually, in all our predictions, said, well, maybe there will be dunes on Titan, but probably not. And it turns out that something like 20% of the surface of Titan is covered in organics, which have formed themselves into huge linear dune fields. And another student is working with me, Chris Savage, looking at analogs to dunes on the Earth to try to better understand the dunes on Titan. And here's a nice analog in Egypt where we see that the dunes approach mountains right here, and they kind of do their best to divert around the mountains and maybe even kind of funnel their way through the mountains. And we see the same kind of behaviors on Titan as well. They try to work their way around topographically elevated obstacles like mountains. We also did some work on mountains trying to determine their elevation and found that a lot of these things are only, a couple kilometers high, several thousand feet, a little bit like from here to the top of Timpanogos if we're lucky, but nothing any higher than that. It's a pretty topographically subdued planet. This is another good analog that we'd like to go and study. This is in Namibia in southwest Africa. And there are huge fields of linear dunes, and they have really the same behaviors in terms of the dunes that we see on Titan. But I guess keep in mind that the dunes on Titan are probably made of organics, so they're almost like hot chocolate materials that have settled out of the atmosphere and then get blown across the surface, made up of organics and dark in color. We've only just finished a map of the global dune orientations, measured 16,000 of these. I guess I'll proudly say I measured 16,000 of these. It was a finish up of work I did as a postdoctoral researcher. And basically we just painstakingly traced out the long axis of the dunes. And what that tells us is how do the winds blow on the surface of Titan? And based on our analyses of the dune interactions with topography, we can also come to the conclusion that the dunes blow mostly from the west to the east, all over Titan. This is the only evidence that we have of what the winds are doing on Titan. The rest is from modeling. So what we do is give our observations and our measurements to the modelers to help them understand what the atmosphere is doing and how the winds are behaving on Titan. And we're also doing some studies. I'm going to go back actually. Right here in this image, this is actually a Hubble Space Telescope image just because it's easier to see these orientations. All the way from the Earth, we can see this really bright feature on Titan, and we call this Xanadu. So it's our stately pleasure dome on Titan, and it's actually been observed from the Earth for many decades. We didn't understand what it was or how it formed, but right now we're in the stages of putting a paper together that should be submitted early this week about Xanadu. And this incorporates all of these new observations from Cassini. And you can see I've got a whole bunch of different radar strips in here. And also there are those infrared images I showed you in the background. Those things tell us about the composition of Xanadu. And then we look very carefully at the geology that we see in those radar images to help us understand what is happening at Xanadu. This is a story that we'll have to sort of stay tuned for. It's very complicated and it's interesting and unique, but we're still kind of working through all the details. I guess I'll just tell you tantalizingly that we have a whole bunch of river channels. You can see a few of them here. There's been lots of river erosion here, and there's also perhaps maybe even a couple of active volcanoes on the southern margin of Xanadu. And we have that evidence both from just the geology and then also from these infrared instruments that show that these regions are hot spots. So Titan might actually be an active planet. We call it a planet because even though it's a satellite, I think of it as a planet in many ways. It has a lot of the characteristics of other active planets that we know of. So we have these huge sand seas, it turns out, all over Titan. But where are the vast methane oceans that we expected to find? Well, once we started looking at the North Polar regions, we found them. We found huge deposits of methane and ethane, lakes and seas, and those are the dark features that you see here. You can see rivers flowing into the one from the south, right here. And this is a fairly big, this is about the size of Kodiak Island in Alaska, a couple of hundred kilometers across. And then here's a false stereo image of that same island showing what it might look like if you were sitting on the surface. It might have that orange tint to the topography because of the hazy atmosphere, and you'd be sitting on a lake of methane and ethane. So we might want to call OPEC because between the dunes and the lakes, we have probably 10 to 100 times the Earth's burnable reserves. So Titan's an interesting place. I don't know if it's really cost productive for us to be able to go and pull these things out and then bring it all the way back to Earth. But we ask ourselves the question of, why is Titan so Earth-like? What is it that makes it have these characteristics that are so much like Earth and yet with completely different materials? And I think we'll have to think about the atmosphere. We've got an atmosphere, we have a fluid just like water, and that might be the biggest, most important factors. So what's ahead for these objects? Well, I mentioned that there's a mission planned for Europa. There's also a mission planned for Titan, and these two are battling it out, and we'll see which one gets picked. And we all really wish that it could be both, but $2.5 billion is a lot of money to come up with. So in the future for Titan, we'd love to send some balloons to work their way through the atmosphere, and also eventually land on Europa and drill our way down. But I would really love to see us go to Io and spend some time on Io and look at the volcanoes and be so close to Jupiter, even though that's a long ways in the future and might be very difficult. But it's been a wonderful adventure so far, and please keep watching for our new solar system observations and our new conclusions, because it's a wonderful solar system that we live in. We're very blessed. Thank you.